about 2.8. So if you just came in, grab it. We're going to spend today and Monday on 2.8. So the first thing we're going to look at is basic operations. And these work exactly like you would expect them to work. If I take a function plus another function at every x value, I'm going to take that f of x plus g of x. Okay? If I subtract two functions, I take the function, the first function at x minus the second function at x. And we'll do some examples when x is a number. But these four operations, addition, subtraction, multiplication, and division on functions, right? We talk about them with numbers, 1 plus 1 or a plus b, the way they work. Now we're looking at functions. What's a function plus a function? What's a function minus a function? A function multiplied by a function or a function divided by a function is going to work exactly like you would expect, right? So there's not really a lot of algebra. Where it comes in the algebra is the composition. You guys heard that term before? Compose, F composed with G. Okay, so that's what we're going to learn about today. An important part of this section is being able to evaluate functions at different points. So you're going to see this again, right? I'm hitting this with a hammer, right? Beating the dead horse, right? You've seen this multiple times. And hopefully by this point, you feel very confident in plugging in t plus 2. If not, we'll do it 50 more times. So bear with me. So yeah, if we're given this expression and we want to evaluate it at t plus 2, this comes up because it's part of the difference quotient, and the difference quotient is a very important concept in college algebra because it comes with slope, which if we talked about the slope of a point, we're going to talk about the slope of a function. So what is f of t plus 2? Right? At this point, you should be comfortable with saying 3 times t plus 2 squared plus 5 times t plus 2 minus 1. Common mistakes here is not writing parentheses around t plus 2. Parentheses are your friend. Parentheses tell you if anything's in front of that, you need to distribute it to both terms. This is not 5t plus 2. It's 5 times t plus 2. Right? So you just take a minute to kind of finish that. And of course, I'll finish it too, but I won't be taking the test. You will, so. Sign and sheet go around, everyone get it? So just to kind of reiterate key things that go on, this t plus 2 squared is t squared plus 4t plus 4. So that's important, but also to keep those parentheses there because that 3 is still out front. So a common mistake there is for students not to distribute that 3 fully. So you should end up with 3t squared plus 12t plus 12. So this is going to come up when we talk about the difference quotient. We're going to have to be able to plug in, and in the difference quotient, we always plug in x plus h. So along the lines of what we talked about with the addition, subtraction, division, and multiplication of functions, this is an example given f of x, g of x, and h of x. What would be the difference of f and g at 3? So this is saying what f at 3 minus g at 3. So I need to evaluate the function f at 3 and evaluate the function g at 3 and then subtract them. Right? So what is f of 3? Well, f of 3 would be minus 2 times 3 minus g of 3, which would be the absolute value of 3 plus 4. So this would be minus 6 minus 7, which gives me a minus 13. So you see how that works? This notation is saying I take the f function and I subtract the g function, and I'm going to do that at the point 3. So f of 3 is minus 6, and g of 3 is 7. So if I take minus 6 minus 7, I get minus 13. Some of you are looking at me like, oh my gosh.
Where did you get the values from?
G, because this function is g, and I plug 3 into the function, which would be 3 plus 4. Yeah, let me know something. I mean, the looks kind of give it away too. Like, what the heck is she talking about? But so yeah, this is calling out that g function or that f function, and this is calling out that g function. They're saying take this function at the point and subtract it from this function at that same point. But you got to be careful when you're subtracting negative numbers or things like that. So you want to make sure you're careful the way you write it. So what is f of 3? Well, f of 3 is minus 6. What is g of 3? G of 3 is 7. So what's minus 6 minus 7, which is minus 13. Half the battle is knowing what it's asking. If you don't know what it's asking, you can't begin to start the problem. So this problem is asking, what is f at minus 1 times g at minus 1? So this is saying, what is f at minus 1? What is that being multiplied by g at minus 1? So I need to find what is f at minus 1, which I look at the f function, and I plug in minus 1. And then I look at the g function, and I plug in minus 1. So that's going to be 2 times 3, which gives me 6. Question?
With the absolute value, would you come up with 2 answers there?
No, the absolute value is always positive.
Okay.
So g of minus 1 was 3. If I said g of minus 9, that would be positive 5, minus 9, right? Because absolute value of a negative number is a positive number. The absolute value of a positive number is just that same positive number, so you drop that absolute value. So you have to evaluate them separately. When we get to composition, there's going to be multiple steps, and it doesn't work the same way. So if you see something like this, it works pretty much like you expected. And an example of that is to look at the graph. So if I give this 1, 2, 3, 4, if I have f of x and I have g of x, and I add them together, how does that affect the graph? Well, here it's the absolute value plus 3. So that's going to take the absolute value graph and shift it up 3 units. So that graph would match to D. What about the absolute value minus 4? Or the absolute value plus a minus 4? That would be the third graph. If I take the absolute value function and I take the minus 4 function and add them together, it shifts it down. This would be 3. This would be 4. Does that make sense there? Not too interesting. It works what we'd expect. So this comes up a lot in college algebra because we want to know information about a function. And one thing about a function is the rate of change. How fast is this function changing? And one thing that's denoted by is the slope. And you guys did this in college algebra. You guys found, or in Math 110, where you guys found slopes of secant lines, right? Knowing 2 points, I can find the slope between those 2 points. The difference quotient is getting very closer. What if I wanted to know the slope only at this point? I could pick a point really close to that point, right? So on the difference quotient, what we do is say, we're going to pick a point x. So that point is x comma f of x, right? And I'm going to then pick an h, where h is a very small distance. And in calculus, you take the limit as h goes to 0 to get the slope at 1 point. That's called a derivative, but you're not quite there. The closest thing we can do to that in college algebra is the difference quotient and saying, well, we're going to take this h value, so this new point is x plus h. And I'm going to plug x plus h into my function, so my new point is x plus h comma f of x plus h, right? And do you guys remember how to find the slope of a line? Change in y over change in x. So this is my x point, and this is my x point, and this is my y point, and this is my y point. So if I do the change in the x, or the change in the y points divided by the change in the x points, right, I would take f of x plus h minus f of x divided by x plus h minus x. You see that? The change in x divided by the change in y. So if I take the y2 point in college algebra, or in Math 110, you call that y2 minus y1 over x2 minus x1, and that's how you find the slope of a line. You guys remember doing that? So what we're doing is the same thing, but we're naming it x and f of x, and f of x plus h at x plus h. So we have these 2 points, x, and then an x plus an h value. That is what's known as the difference quotient right there. F of x plus h minus f of x divided by h. And in this case, when you set it up this way, your h in your denominator always cancels with something with an h in the numerator. So you always have to be able to factor out an h in every term. If it doesn't happen that way, you didn't set it up correct. So there's a kind of nice little, you know where you're going to end up going to. You're going to cancel all the terms that don't have an h in it, and then you're going to factor out an h and cancel the h in the denominator. So let's look at an application of this. This is a line, 5x plus 9. Do you guys know what the slope of this line is? This is a line, right? Y equals mx plus b. You guys remember that? So this function has a constant slope. It's 5. The difference quotient should be 5 because that is what the difference quotient means. It means the slope at any point. So if it's constant slope because it's a line, so it needs to be 5. The example we'll do over here, this doesn't have a constant slope because it's a quadratic. So the slope is going to depend on x. The slope at any given point, if I just kind of graph a quadratic real quick, sometimes the slope's negative, sometimes it's positive, sometimes it's 0. Got a lot going on there. So the slope at any point is a function of x. right? So that's where we're getting along. But any line, the difference quotient is always the slope because that's what it means to be difference quotient. Right? So let's set this one up. So the first thing we need to do is find f of x plus h. So I have 5 times the quantity x plus h plus 9, which would give me 5x plus 5h plus 9. It's kind of the first part in finding the difference quotient is finding f of x plus h. This is part A. Part B is to set that up in the difference quotient. So this is going to be f of x plus h minus f of x. And I'm just going to highlight this. And when you get to an exam, you might want to kind of circle this to know that you're going to distribute this negative to every term in f of x. It's a very common mistake here, is not distributing that negative properly. Divided by h. So if I plug in f of x plus h, that's what I found here. So I can plug that in. Minus, open parenthesis, the function 5x plus 9, close parenthesis, over h. So you guys see how this, ooh, I lost my minus, or my plus 9. Plus 9 minus 5x plus 9. So this here is f of x plus h. This here is f of x. And then I have that divided by h. You see the setup? Now I'll tell you, everything on the left side, sorry, the right side, everything on the right side of the negative side is going to cancel with something on the left-hand side. It has to, because there's no h's. And I've already told you that I have to be able to cancel this h. So if I distribute this negative, I'm going to go ahead and write this down here. I have 5x plus 5h plus 9 minus 5x minus 9 all over h. I have to distribute that negative because if I don't, I have 9 plus 9, which is 18, and that doesn't have an h in it. And I've already told you every term that does not have an h in it will cancel. So that's just another helpful reminder to distribute that negative. So now my 9 plus 9 and minus 9 cancel. My minus 5x and my plus 5x cancel. And I'm left with 5h over h. That cancels to 5, which is exactly what we expected, right? It's a leading to calculus. This is the definition of the derivative. That's a big part of calculus, being able to find the slope at any given point in time. And in calculus, when you have a function, we've already kind of talked about maximum and minimum points. What do you notice about those maximum and minimum points? What about the slope? The slope is always 0. Anytime you have a maximum and minimum point, your slope's always going to be 0. So if you can find the function for the derivative in function terms, you can set that equal to 0. Boom, you found all possible maximum and minimum points for that function, which is a big concept in physics. If I have a position function, then the derivative of position is velocity. If I can find when is my particle stopped, I can find out when it's slowing up and speeding down. I can find a lot from it, from just knowing the function. Here, the slope's constant 5. So there are no maximum or minimum points, which if I was to graph this is exactly what I expect. I have a line that goes through the point 0, 9 that has a slope of 5. There's no maximum and minimum points there. It just keeps going. The slope is always 5. It's constant. So that's why we got a constant number there. This example, it's going to have one critical point. It's going to have one either maximum or minimum because it's quadratic. But to be able to find that, we could find the slope at any given point in time. So that's going to be a function of x. So we're going to find out what x value does a vertex exist. So we have to still do the difference quotient. F of x plus h minus f of x over h. So part A is to find f of x plus h. That's going to be x plus h squared minus 3 times x plus h. You guys see why now you did the 3 plus t and the a plus 9 into the functions? Because now you evaluate that function of x plus h, I end up with x squared plus 2xh plus h squared minus 3x minus 3h. And you have to be careful. You're distributing that minus 3 to both those terms. So does everyone see where this f of x plus h came from? I plug x plus h into my original function of x plus h squared minus 3 times the quantity x plus h. So now to do the difference quotient, the difference quotient we have listed here. I already have the x plus h, so I'm just going to write it. X squared plus 2xh plus h squared minus 3x minus 3h. Minus, open parenthesis, then I write the original function. X squared minus 3x. X squared minus 3x. Here, if I did not write the parenthesis, I would know something was wrong because minus 3x and minus 3x is minus 6x. I know I have to cancel those. So I need this negative to be distributed. Once it's distributed, this cancels with this cancels with this. And do you see how all the terms that are left have an h in them? At least an h in them? You will always cancel everything on the right side of your x or your minus sign. So now, if I go ahead and factor out an h, the terms that are left, I have 2x plus h minus 3 divided by h. The h's cancel, and my answer is going to be 2x plus h minus 3. So what this is saying is the slope at x equals 1 is going to be plugging 1 into this function, which would be minus 1. The slope, because h goes to 0. And that's what you do in calculus, is you take the limit. Remember, h is the distance between x and x plus h. So if h went to 0, that would give me the slope at 1 point, which is the definition of the derivative. So you don't have to know the application of this. You just have to be able to be comfortable with doing it. So knowing the foresight where you take f of x plus h minus the function, all the terms in that function are going to cancel with terms in the f of x plus h function. It has to happen that way. If it does not happen, you made an algebraic error in the step above it. Then you're only left with h terms. So if you factor out that h, then you can cancel the h in the denominator, and then you're left with a equation. Right? Let's go to Alex, since we're going to spend 2 days on this section. Before I get to compositions, I want to pull up Alex type questions and then do some of those in class. Open the student view. Submit this homework. I don't have the best Alex grade. So being able to go into 2.8. So you can see the first question is a difference quotient. So calculate the difference quotient of 2x squared minus 1. Two x squared minus 1. See what you guys get. So the first thing you need to do is find what is f of x plus h, because that's your first set of terms in the difference quotient. So you guys are going to have to do this eventually for your homework, and will be on your exam. I'll throw something down and see how it works. Good. You also have a 2. You have those 2 terms. Good. That is your answer. So remember what I said, this plus 1 and this minus 1. Anytime you get down to a point here, you have every term in the numerator has to have an h. So this doesn't have an h. So you know probably something along there. You have a minus 1 here. And you have a plus 1 here. So they're distributed. Gotcha. Good. So you're really close.
Like, I don't understand this part, like, the very last term, 2x squared minus 1.
Because that's what the x is, like up here, it's 2x squared minus 1, so then
You're really close.
with the, you plug it in, like in the beginning, but then like right here, you just put it right there.
So do you guys kind of see how it works?
So, so because this is,
Oh,
So that's what x is.
so
Close
this
to the problem,
little,
but yeah.
this whole little thing
That's
is
okay.
what x is.
So,
That's what I don't understand.
yeah, so
I
good.
I get to there.
Good.
I don't really understand what that means right here, that,
This f of x, that's the original function.
okay.
The original function is 2x minus 1. So if I kind of code what I have, this is f of x plus h, and you calculated that perfectly. This is f of x plus h. That's what you want. Then I subtract f of x, which is just whatever my function is to begin with.
Okay.
I don't manipulate it in any way. I
that
leave it.
Part, the
Mhm,
minus f
mhm.
of x is always going to be what your original.
Yes.
Like you were saying. Okay.
Yes.
Thank you.
So yeah. So then you simplify it. So at this point, I know both these terms have to cancel because they don't have an h in it. Right? So I have this minus 2x squared. If I write one extra step out, 2x squared plus 4xh plus 2h squared minus 1 minus 2x squared plus 1. So I need to make sure I distribute that. It's a common mistake when students don't distribute that. Then they end up with like 2, or they end up with another term. So this minus 1 and plus 1 cancel. This minus 2x squared cancels with this plus 2x squared. And I'm only left with 4xh plus 2h squared over h. That cancels, that cancels, that cancels, and I'm left with 2x plus, thank you, 4x plus 2h. Right? So the slope at any given point, if I say x is 2, and I want to know what the slope would be at 2, I would say, okay, I'm going to look at the secant line at 2 and 3. And so my h would be 1. Well, now I'm going to look at my slope, my secant line at 2 and 2.5. So my h is 0.5. Now I'm going to look at the secant line at 2 and 2.25. So it's only a quarter then. And it gets smaller and smaller. And then once you learn in the power of calculus is actually make h go to 0. And then you can find the slope at any given point. So this is really, really close to calculus. I teach an online version of calculus, and students struggle with this because they don't understand the algebra. They can do the calculus just fine because that's just applying a very basic concept, plugging in a point. But it's the algebra that gets them, and it's the algebra from the difference quotient. So we have 2x, or we have 4x plus 2h. So if I go to Alex in here, it should accept the 4x plus the 2h. It's not going to tell me if it's right or not because I have to do the whole homework problem. Here's the example where I was talking about before. Write the expression for r plus x. This is the expression. So I'm not plugging in a point. I'm plugging in the expression. So let's look at pulling that up on. What would be the expression for r plus s? Yeah, so I would have 3x minus 2 plus 6x. Simplifying that would be 9x minus 2. What would be r times s? I'd have 6x times the quantity 3x minus 2. 18x squared minus 12x. Right, because I just distribute those terms. What about r minus s? Yeah, so the r is positive, but the s is negative. So r minus s is 3x minus 2 minus 6x, which would end up being minus 3x minus 2, simplified. Right? Exactly what you'd expect. No, nothing surprising there. Here, the question is asking you to evaluate it at 1. So be a little careful there. It's saying r minus s. What's r minus s at 1? And if you found this, you can plug in 1 here, or you can take what is r at 1 minus s at 1, and you'll get the same answer. So what is r at 1? Is it 1? And then s at 1? So this tells me minus 5. What if I plug 1 in here? I get minus 5 as well, right? Which is what you would expect. This is the general term for r minus s. So r minus s at 1 is minus 5, but I could also take what is r at 1 minus what is s at 1. So putting those in should be pretty straightforward. So this next question leads us into being able to calculate f of x over g of x, or in this case, h of x over g of x. And everything's going to work the exact same way, except we have to be very careful for our domain that g of x can't be 0. Right? That's the only thing we have to worry about. So if I take this question and I say I have these two functions, and what is h of g, or h divided by g at 5, it's going to be h at 5 divided by g at 5. So I have 4 plus 5 times minus 5 plus 5 over 8 minus 5, which would be 0 over 3. What is 0 over 3? 0. There's no problem with that. The problem if 0 is in the denominator. So this approach is saying, can you evaluate this division of functions at the point 5? And then it says, list all the values that would not be in the domain of the function. Right? If I have a function h of x over g of x, what values are not in the domain? That would be the values in which g of x would be 0. Right? Because 0, the denominator can't be 0. So when is the denominator 0? At 8, right? I have problems when my g of x equals 0. So I know x cannot equal 8. So my domain here would be minus infinity to 8 union 8 to infinity. Right? It's going to get more complicated when we talk about compositions, but for right now, it works the way you would expect it. You don't have to worry about domain and range when you're adding, subtracting, or multiplying. You only have to worry about it when you're dividing it, and you only have to worry about the function that's in the denominator. You want to make sure that function can't be 0. So in this case, it just asks you to list the values that aren't in the domain. So you just write 8 there. So depending on how they word it, if they want you to write your answer in interval notation for the domain, you would write minus infinity to 8 union 8 to infinity. But here they're just asking you to list the values that are not in the domain. So here we have f of x plus g of x. So you're going to add those two functions together. It's going to work in a function of x. So you have this function plus this function. If I want to write that in there, I have 2x plus 5 minus 2x plus 5 plus, then I take my fraction, my fraction form, 1 in the numerator, then I have to get my square root, 4x minus 1. The domain of f plus g is where the domains overlap. So f of x, I have no problems, right? G of x, I have problems. So my domain of this function is going to have problems when g of x has problems. You can't add a problem to a number. So you would need to solve for when there's a problem here, and that's going to be the domain. It's going to be where they overlap. All right, no problems, and then problems with g of x there.
You don't have to solve the whole thing. You don't already
That is already done. That is f of x plus g of x is the f of x function plus the g of x function. Typically they might write it, what is f of x plus g of x at 1? Then you plug 1 into this expression and get a number. But this is the answer here. Is how would I write this as one function? Well, you take the first function plus the second function. The domain is going to be where the domains overlap. The domains of two functions, they have to both exist in those domains. Not one can't exist and one can, right? Because a does not exist plus a number doesn't exist. And the same thing with the multiplication. So setting that up, you just take, and there's a couple different ways you can write it. Both, Alex should accept anything that is correct. So if I multiply these two functions, I end up with 4x minus 1. Again, it's going to be where the domains overlap. So the domain here is going to be the same. So this is going back to our notes. Alex starts introducing this idea of a composition function. And composition, you guys, how many of you had exposure to compositions before in some form? 1, 2, okay. A composition function is taking something, manipulating it in one way, taking that thing that's been manipulating it a different way and getting an output. So it looks a lot like multiplication, but it's not. This is how it'll be denoted, or it could be denoted this way. What this is saying is I take x, I plug it into my g function, and I get something out. I take that something that I got out of the g function, and I plug it in the f function. Or it can be written as g of f of x. So order here matters. When addition, subtraction, that's going to work just like you would expect. 1 plus 5 and 5 plus 1 is going to be the same thing. Here, composition is a little different. So let's just kind of, your book has this little picture. You put in x into g. You get out g of x, right? Whatever that is. Then you take g of x and you plug that into f, and you get out f of g of x. So to begin this, your book starts with numbers. They give you 3 different functions here, and they say, what is f of g of x? 8. So what this is saying is I take g of 8, and I plug this into the f function. Right? So what is g of 8? Yeah, so g of 8 is the square root of 2 times 8, which is the square root of 16, which is 4. So this is saying I take f of g of 8, but g of 8 is 4, so I take f of 4. So what is f of 4? 4 cubed minus 4 times 4, which is 48. Question?
Why do you plug it into the g of x?
Because the g of x is the innermost function. You always work inside out. So this is, I take 8, I put it into g, and I get out 4. Then I take 4 and plug that in f, and I get out 48. So let's look at the second example here, h of f of 1. That is saying, what is f of 1? I'm going to take whatever f of 1 is, and I'm going to plug that into h. So f of 1 is 1 cubed minus 4 times 1, which which is minus 3. So then I'm evaluating h at minus 3. Which gives me minus 6 plus 3, which is minus 3. So you see how f of 1 is minus 3? So I take f of 1 as minus 3, and then I plug that minus 3 into h function, and I get out minus 3. What about the composition of f and h at minus 1? So this is just written a little differently. What this means is f of h of minus 1. So when you guys get these two right, I'll let you out of here. So I have the answers and I'll walk around. Sign your sheet and make it around. I think some people got it. Yes, it is the same thing. Order doesn't matter. Get it? That is correct. So try this one. That is correct. Yeah. Good. Yeah. Yeah. You can leave it.
It's cubed, I'm like, okay.
Yeah. This is an exact number, not the composition. Right? It's like not knowing
Exactly.
but a lot of times in here, I wasn't talking.
Right.
14 foot.
Point.
I know what 14 foot is in my head, but I don't know what the square and okay.
So am I good to go?
Yeah. Where's your answer? Yes. Okay. Yeah, so just a little bit on notation. It's not f of x. So h at minus 1, you got this minus 3, right? Then you plug minus 3 in to f, which was, yeah, I can't see what you're doing too well. 1. Okay, 1. H of minus 1 should be 1. You got that here, 1, and you plug 1 into this function that minus 3 here. Yeah, just the notation is your control. You might want to write, like, okay, so you got this 1 here, so then you say this equals f of 1. Okay, and then that tells me you got the 1 from this. This is just on the outside. Right, so like I have here, and then I say, okay, well, what is h at minus 1? H at minus 1 is 1. So now I'm looking at f at 1. And that's my answer. So then this would be minus 3. You can do the work on the side if this is going to be the end that I understand. You first found h at minus 1 is 1. Then you plug that into f and got minus 3. And then the same thing here. F at 5, and I can see that there, and you got 105. Then you plug 105 into the g of x function, and you got that. So if you were to g of 105, it is. It really is. Because it will come in more importantly because they will
Alrighty.
You girls get it?
I didn't.
Good. No, good. That's very good. Yeah. You took that, you did that. That's perfect. Great notation. Very easy to follow. Good. Very good. Nice.
Now, if I remember if it says.
Question? So, good, good. So all that's good. All that's good. What you have all there is good. Just one extra step.